All right, here's another example of using the individual graphs, x versus t and y versus t, to figure out what the graph of the parametric equations are. What the graph is, I guess. I have an example here that I think we've seen before. X equals cos t, y equals sine t. Particularly, we've seen it before because if you think of t as a central angle, I'm describing points on the unit circle, right? If you got an angle in standard position, then the x-coordinate is the cosine of the angle and the y-coordinate is the sine of the angle. Right? But now I see this way, where x, right, the x-axis is running this way and the t-axis is that way, so this is kind of a sideways graph so that the x-axis lines up with the x-axis here. As t goes on, x goes from 1 down to -1 back to 1 and then repeats itself. At the same time, the y-coordinate is a sine curve starting at 0, going up to 1, coming down to -1, back to 0. So as the x is moving back and forth, the y is going up and down, and the net result is a circle. Right? Remember, the red is just moving horizontally, just moving back and forth. It's giving you the x-coordinate. The blue is just moving up and down, just giving you the y-coordinate. For each value of t, you figure out x, you figure out y, you plot the point. And I'm just showing you all of them at the same time through an animation here. Okay. Now, there's several things that I want to point out here. We could show that this is, in fact, we did show that this is a circle, right? We eliminated the parameter by squaring both sides here and then adding them up. But there's other kind of nifty things I'd like to do. For instance, if I were to take this right here and multiply by 2, so y equals 2 sine t, well, I can look at this equation, this graph down here and say, well, that would just change the amplitude, so this should go up to 2 and down to -2, which should just pull this up to 2 and down to -2, and we can see that that circle then is just stretched into an ellipse. I'm going to zoom out a little bit here. So now the x-coordinate is still moving back and forth between 1 and -1. But while it's doing that, the y-coordinate is going bigger up to 2 all the way down to -2. This is indeed an ellipse, and we will show in a subsequent video do the eliminate the parameter process to come up with the equation of that ellipse. But it really becomes pretty easy to draw ellipses of any size and shape here. Just by saying, hey, I need to stretch it by 2 in the y direction, or maybe I need to stretch it by 7 in the x direction, right? All of a sudden I got a really long ellipse going that way. Let me zoom out so maybe I can see things a little better. Right? And so now I've got the x-coordinate going between 7 and -7, and the y-coordinate going between +2 and -2. So that's stretched that unit circle into an ellipse. Other things I can do is say, I don't really want the center at the origin. I want to shift it over a little bit. Let's shift it in the x direction over 1. Well, if I want to take all these x values and move them over 1, then that's making them all 1 bigger than they used to be. Let's just add 1 to this. Let's just say 1 plus 7 cos t. You notice as I change that from a 0 to a 1, the graph just shifts over accordingly. Right? You want to change the y-coordinate of the center? Well, add it on to whatever you wanted here. So let's say plus, let's shift it down 3. Right? The center now of the y's is at -3, with amplitude 2 goes up to 1 and down to, -1 to -5. The x-coordinate here is centered at 1 with amplitude 7, so it gets as low as -6 and as high as 8. Right? There you go. It's really easy parametrically to get the ellipse you want. You can put the center and then just do this stretched out unit circle. Right? Other variations here is this is rotating around clockwise. No, this would be counterclockwise. If I wanted it to go clockwise, there's a couple ways I could do it. One is thinking of this here as starting off at the, at time 0, you're at the highest x value and the middle y value. Well, if rather than starting here and going up, you wanted to start here and go down, well, then I have to take this sine curve and flip it upside down. Well, do I know how to flip a sine curve upside down? Yeah, I do know how to flip a sine curve upside down. I just have to give it a negative amplitude here. Flip that thing upside down. I'm still describing exactly the same. Watch what happens here. With a plus sign or with a minus sign, that ellipse over here is the same ellipse. It's just a matter of, is the y-coordinate starting here and going up, or is the y-coordinate here starting here and going down? If I start here going down, now I'm tracing that ellipse out in a clockwise fashion. There's all kinds of different ways you can represent this same ellipse, rotating clockwise, rotating counterclockwise. We happen to be starting over here because we have a cosine here, and if we wanted to start, let's say, at the top, at the highest point, then it's the x-coordinate that is starting in the middle. So let's make that a sine, and it's the y-coordinate that's starting off at its highest point. So let's make that a cosine. Actually, let's make it a positive cosine. Okay. I still have the same ellipse that I had before, but now at time 0, I started up here. Right? The relationship is still the same. In fact, we'll have to show that in the next video. I'm describing the same ellipse, but I'm describing it from a different starting point. And in this case, I'm doing it in a counterclockwise fashion. If I wanted to go clockwise, let's start up at the top and go this way. So my x's would have to start at 0 and go negative here. So we got to take that and turn that into a negative there. Notice that it switched the x graph around. And now I'm going in the opposite direction. Okay. All sorts of ways you can parameterize that ellipse. All right, let's stop here and switch over to the algebraic side here and do some eliminating of the parameter on this.